All right, let's dive right into one of the biggest, most famous unsolved problems in all of mathematics, the Riemann hypothesis. This is a story about finding a secret, hidden order in what looks like the total chaos of prime numbers, a single rule that has stumped the greatest minds for well over a century.
So, you got to ask yourself this central question right away. How is it even possible that trillions, and I mean trillions of these seemingly random numbers, all fall perfectly into place, following one hidden rule? That is the grand mystery we're talking about today. And you know, this isn't some brand new puzzle we just stumbled upon. We're talking more than 160 years. It's like the Mount Everest for mathematicians. But what's so exciting is that a new way of looking at it, an idea borrowed from the world of physics, might finally give us the map we need to reach the top. So let's break it down.
Okay, but before we jump into that new idea, we really need to set the stage. You have to get a feel for just how deep and just how old this mystery truly is.
So it all kicks off back in 1859 with a mathematician named Bernhard Riemann. By 1900, it was already so famous it made it onto this legendary list of 23 massive unsolved problems. 100 years after that, in the year 2000, it's named a Millennium Prize problem. There's literally $1 million prize for anyone who can solve it, and it's still just sitting there unclaimed. And here we are, still totally captivated.
So what's the big claim? What's the hypothesis actually say? Well, it sounds almost too simple. It says that all of the important solutions, and in math speak they call these non-trivial zeros, to a very special function all lie on one single, perfectly straight line. And I mean perfectly, not just kind of close to the line, but dead on it.
Now, to really get why this is such a huge deal, there's this fantastic analogy. Instead of thinking of prime numbers as just random noise, imagine they're actually a kind of hidden music. And this is where it gets really cool because it connects these two completely different worlds. Think about music, right? You have all these complex vibrations, but they resolve into these beautiful, clear harmonics. The idea here is that prime numbers do the exact same thing. That messy, complex vibration, that's something called the Riemann zeta function. And those clear, important harmonics, those are our non-trivial zeros. And just like musical notes have to hit very precise frequencies, the hypothesis says these zeros have to line up perfectly on what's called the critical line.
So everything really hinges on this zeta function. The best way to think of it is like a cosmic instrument. Don't worry, we're not going to get bogged down in the crazy formula. All you need to know is that the notes this instrument plays, those zeros, they somehow hold the secret to the entire pattern of the prime numbers.
Now, for a long, long time, mathematicians have known there was something special about this instrument. It has this hidden property, a deep secret that controls everything it does. And that secret is a perfect symmetry.
What do I mean by symmetry? I mean it's a perfect mirror image. Whatever happens on one side of that critical line is perfectly, exactly reflected on the other side. This isn't a coincidence. It's a fundamental rule that is baked right into the DNA of the function itself.
This rule has a fancy name. It's called the functional equation. And here's the crucial takeaway. Because of this perfect symmetry, if, and it's a big if, a zero were to exist off the line, it absolutely has to have a mirror image buddy on the other side. They come in pairs. It's a package deal. You can't have one without the other. Seriously, remember that part, because it is the whole key. Okay, so we've got this perfect symmetry, this package deal. Now, let's bring in that new perspective I mentioned. This is where things get really interesting, because we're going to start looking at this whole thing not just as a math problem, but through the eyes of a physicist, thinking about energy.
So let's imagine a super simple rule. We'll call it an energy measurement. All it does is check how far a zero is from that perfect critical line. So if a zero is right on the line, its energy is zero. Simple enough. But if it wanders off the line, it gets some positive energy. The line itself is kind of like the ultimate state of rest, the lowest possible energy state.
And here is the big aha moment. That symmetry we were just talking about, that mirror image rule, it's not just some neat pattern. It acts like an unbreakable law of physics. It literally forces the entire system, all of the zeros combined, to settle into the lowest possible energy state it can find. And what is that lowest state? Well, it's zero.
Okay, this is it. This is the heart of the whole argument. Let's just walk through it step by step. 1. Let's pretend for a second that a zero does go rogue and wanders off the line. 2. That symmetry rule immediately kicks in and says, nope, you need a mirror image partner. So now you have a pair. 3. This pair, because it's off the line, creates a little bump of positive energy. 4, and this is super important, the math shows these energy bumps can never,
ever cancel each other out. They always add up. But step 5, that very same symmetry rule also demands that the total energy for the whole system has to be 0. So, you see the problem, right? You have these energy bumps that can't be canceled, but the total has to be 0. How is that possible? There's only one way. Step 6. Those offline zeros can't exist in the first place. The whole idea creates a contradiction.
And that leads us to this incredibly powerful conclusion. The zeros aren't on the line just by chance, or because we've checked a bajillion of them with computers. If this argument is right, they have to be on the line. It's a necessity. The famous hypothesis isn't some random quirk, it's a direct, unavoidable consequence of that deep symmetry that's baked right into the function.
So that's a really elegant, beautiful argument, but let's bring it back. What does this actually mean for the prime numbers themselves? Why should we care? Why does all of this matter?
Well, the implications are just huge. If the Riemann hypothesis is true, it means that prime numbers, the fundamental building blocks of all of arithmetic, aren't just scattered about randomly. They actually have a deep, hidden structure. To put it perfectly, primes are as regularly distributed as they can possibly be.
What does that actually mean? Well, you can think of that perfect line of zeros as a kind of master control system. It sets the absolute hard limit on how far the prime numbers can ever stray from their average pattern. It puts the tightest possible leash on their seeming randomness, and in doing so, reveals this incredible, hidden order. And look, the evidence we have is just staggering. We've used computers to check more than 10 trillion of these zeros, and every single one, without exception, is sitting perfectly on that line. But here's the thing. Checking a bunch of examples is not a mathematical proof. What this whole energy idea tries to do is finally explain the why, the reason behind what our computers have been screaming at us for decades.
And that leaves us with this one last incredible thought. Prime numbers are absolutely fundamental. They're part of the language the universe is written in. And if something that basic is governed by such a deep and elegant symmetry, basically a law of minimum energy, it just makes you wonder, right? What other huge secrets are out there, hiding in physics or biology or even information itself, just waiting for us to find them, all following a similar, beautiful, perfect line of order?